In this video, we're going to kick off our work with linear functions by talking about slope. Before we get into the technical details of slope, we want to look at this image, and I want to know which line is steepest. Go ahead and select your answer. All right. Now, if we have some more information, which line is steepest? Has your answer changed? So when we talk about slope, slope is the measure of the steepness of a line. And we have several different lines here, and these demonstrate positive slopes. So think about if someone was walking up a hill, that would be a positive slope. And they could be walking up a relatively flat incline. They could be walking up a relatively steep incline. But anytime they're going uphill, again, always going from left to right, that's when we talk about a positive slope. On the other hand, we have negative slopes. So that would be if I'm going downhill. Again, moving from left to right, and it could be a pretty flat downhill or a pretty steep downhill. But anytime we're walking downhill, that would be an example of a negative slope. When we talk about that steepness, we can see that as this line goes further and further towards vertical, that's more steep, and that could be in the positive or in the negative. And as we get closer and closer to a flat line, that would be less steep. So we talk about the change as we go up versus the change as we go over. In this case, the change as we go down versus the change as we move to the right. We also have some special slopes where we could have a slope of 0, and that would be where you're walking along that flat surface with no incline. Or we have undefined, where you really can't walk at all because it's just a sheer cliff, so you're just falling. That's not good. Look at why those are the way that they are in a little bit. So now we're going to get more into the technical aspects of slope. So first thing, slope is a ratio comparing the vertical change to the horizontal change in a line. So the way that we find this, we compare that vertical change, how far we move up and down the y-axis, versus that horizontal change, how far we move side to side. Remember that the y-axis is our vertical axis, so vertical change is change in y, and the x-axis is our horizontal axis, so horizontal change is change in x. And the names that we typically use for these are rise and run, so oftentimes you'll see slope designated as rise over run. And it's always going to be the comparison of vertical change in the numerator in the top to horizontal change in the denominator. Always rise on top and run on the bottom. And if we're given a graph, it's very simple to find the slope between any 2 points on the line in a graph. Again, I'm going to work my way from left to right. And so we can start with this point here. I'm going to start with my rise. So in order to get from point A, we'll call this, to point B, I need to see how far up do I have to move, or down. In this case, we move up 1 unit, so my rise is going to be 1. Then we see how far to the right we have to go. So that's my run. So we count 1, 2, 3, 4, 5, 6 units. So my run is 6. So my rise over run is 1 over 6. If we got something that needed to be simplified, we would go ahead and do that. But this means that for every 1 unit we go up, we move to the right 6 units. If we look at this next one, we're going to move, we'll say this is point A to point B. Again, moving from left to right. We can do it backwards, but for now we're going to stick with left to right. And now I have to go down. So I'm going to come down 3 units. So my rise is going to be -3. And now I have to run forward another 3 units. So we simplify that. -3 over 3 is going to give me a slope of -1. If I look at these two lines, I can see that my first line isn't nearly as steep as my second line, even though we have a change from uphill to downhill. If we look at the absolute value of the slope, that will help us compare steepness. So here we have an absolute value of 1/6. Here we have an absolute value of 1. So that means that this line is the steeper line. We can also find those special slopes on the graph. So if I look at this one, to get from point A to point B, I don't have any vertical change. We're not moving up or down at all. We're just going flat. So my rise is 0. Now if I look at my run to get from point A to point B, we go 1, 2, 3, 4 units to the right. And we know that 0 divided by anything except for 0 is just going to be 0. So our slope here is 0. So the slope of 0 is always going to give us a horizontal, forgot the T there, line. If we look at this next one, again, we'll pick this one because they're both stacked on top of each other, point A to point B. So my rise, I go down 2, so that would be -2. And then my run, I don't move side to side at all, so my run is 0. And remember that we can't divide by 0. Anytime we divide by 0, that answer is undefined. So this is a slope that is undefined. And that is always going to be a vertical line, because there's no horizontal change. All the x values are all the same. There's no change. Here, all the y values are the same, so there's no change. So these are two special types of lines, and because there's a lack of change in either the rise or the run, we get those special slopes. So we're not always going to have a graph that we're going to use to find slope. Sometimes we're just going to be given 2 coordinates, but it still comes down to that idea of change in y and change in x. So I'm going to use a graph to help explain where this rule that we're going to use is going to come from. So I have my first point, 2, -3, and then our other point is 6, 3. So over 6, up 3. And now if we draw in that line here, all right, so we can find our slope, same as we've been doing. So I'm going to rise up 1, 2, 3, 4, 5, 6. And now I'm going to run 1, 2, 3, 4. And we would reduce, and we would get 3/2. When we talk about change, we're talking about what's different. So when I find these points, if I didn't have the graph to help me out, my change in y is going to be the difference between my 2 y coordinates. So I'm going to go with my second one because that's where we ended up, and I'm going to subtract my first one. And that's going to give me my change in y of 6 units. We can do the same thing in the denominator, so change in x. We ended up at 6, and we started at 2. Don't need parentheses there, I don't know why I put those in, and we get 4. So again, we get 6/4, which reduces to 3/2. So we're finding the difference in those coordinates. I could do this the other way too. If we had 3 or -3 minus 3 over 2 minus 6, -3 minus 3 is -6, 2 minus 6 is -4, and that still reduces to 3/2. All right, so it works either way. So we can try it down here. I changed my y coordinates, so I went from 2 to 2, so we're going to find the difference. Then my change in my x coordinates, we went from 5 to 3, or from 3 to 5, so we're going to find the difference. So we end up with 0/2, which is just a slope of 0. Because as we can see, those y coordinates were the same, which meant there was no vertical change. Go ahead and pause the video and see if you can find the last slope. Oh, actually, hold on, I forgot to change those coordinates out. We'll switch those out. Let's do 4, 7. Sorry, that's getting a little sloppy there. Let's do 4, 7. And let's do 2, -9. Go ahead and pause the video, see if you can find the slope between those 2 points. All right, so we're going to do the same thing. Find the difference in the y's. So -9 minus 7, and the difference in the x's, 2 minus 4. -9 minus 7 is -16. 2 minus 4 is -2. -16 divided by -2 is 8. So we end up with a slope of 8. And oftentimes we'll use the variable m to represent slope. So anytime you see m equals, you just want to keep that in mind. That's going to mean that we're talking about slope. So here's that formula that we've talked about, right? So if I have 2 ordered pairs, if I have x1, y1, and x2, y2, this would be the formula that we were just using to find slope. the difference in the y's, and this change in y, sometimes you'll see that delta y, delta means change, and the change in the x's. Sometimes you'll see that as delta x. These subscripts here don't do anything mathematically, they're just a label telling us that this is the first point and that this is the second. Sometimes we're given information and we're asked to find a missing coordinate, so we're going to come to our slope formula in order to do this. So we want to determine the value of x so that the line between these 2 points has a slope of 4. I'm going to come back to my formula here. So y2 will make this our second point, we'll make this our first point. So the second y coordinate would be -7 minus the first y coordinate, which was 9, divided by the second x coordinate, which is our unknown, minus the first x coordinate, which was -15, and that's all equal to 4. So the first thing I'm going to do is simplify my left side. So -7 minus 9 is -16, x plus 15 on the denominator, and that's all equal to 4. Well, this is the same thing as 4 over 1, and now we have a proportion, so we can cross multiply. -16 times 1 is just -16, and that's equal to 4 times x plus 15. So we can keep going. We get 4x plus 60, and we can continue to solve. So -16 minus 60 is -76, equal to 4x, and if we divide that out, we'll get that x equals -19. Go ahead and pause the video and try the second one on your own. Alright, so again, we can label our 2 points, x1, y1, x2, y2, and we have our slope here. So we can set up our equation, the difference in the y coordinates, the difference in the x coordinates, and that's equal to our slope, get our proportion, and we solve, and we get a y value of 1. You'll also see slope referred to as the rate of change, and this is when we talk about it more generally in context as a change in a dependent variable, which remember is always our y, and the change in an independent variable, our x. And we could have rate of change in lots of different functions, but in linear relationships, the rate of change is constant. This means that it's always the same. So if I look at this table, it shows the distance a marching band marches over time. We want to know, is the rate of change in distance with respect to time constant? Is it the same? And what does that rate of change represent? So I'm going to look at this in increments. So from 1 to 2, the rate of change, delta x, equals 1. And from 260 to 520, the rate of change, delta y, equals 260. So our rate of change is change in y over change in x. That equals 260 over 1, and that equals 260. So if this is constant, every time we do an interval, we'll get the same thing. So we'll go to the next one, 2 to 3. The change in x again is 1. Then the change in y from 520 to 780, that's 260. So again, our change in y over our change in x is going to be 260 over 1, which is 260. So we still have to check the last one because we have to make sure that this is constant all the way through. So here from 3 to 4, our change in x is 1. From 780 to 1040, our change in y, delta y, is 260. So again, our change in y over our change in x is equal to 260 over 1, or 260. So yes, this is constant. I'm going to abbreviate the rate of change is constant, which means that this relationship is linear. So if I were to graph this, it would be a line, and since it's positive, our line would be increasing with a positive slope. And this means that for every minute that we walk, or every minute that goes by, the band marches 260 feet. So if we wanted to find the slope of this, I can just treat each row in the table as an ordered pair. It doesn't matter which two I pick, and we can use that slope formula to find the rate of change or the slope.